Hey guys, Eco here. I want to go over Region 3 rotation today because it's worth learning and there's some interesting stuff in it. Now I've seen some pretty crazy modules before, or at least one by axis angle, and this is not that confusing. And to my knowledge anyway, I'm not gonna lie, I haven't really read through too much through his stuff because it is just a huge, like, practically a thesis paper of code there. So I haven't really read through it, and it is crazy good from what I saw, but there are definitely some limitations that I can see anyway. So I mean, once again, didn't read it, so maybe there's some things that I'm missing here, but to my knowledge, my method seems pretty good. So I'm quite happy with it, and I think there's definitely benefits to it over his. That being said, let's go over first off what the problem is. So this is, for all intensive purposes, a perfectly aligned shape. So I can say this is like the Y component, this is the X component, and this is the Z component. And it's pretty straightforward. I mean, you have some point down here, and you have some point up here is basically the idea. You get this point here by applying the size to this point here, so some size vector which gets you up to this point, and then you have a box, and you want to find all the points and what have you inside the box. So it's a pretty simple idea. I mean, you can kind of go over the simple form of the math anyway. We can say this point is going to be, we'll say Q, and this point will be R. And we can say that the actual point inside is P. So we'll say if, Q sub X is less than or equal to P, or I suppose this would make it a little easier for me anyway. I say P sub X is greater than or equal to Q sub X, and P sub X is less than or equal to R sub X. Sorry. And P sub Y is greater than or equal to Q sub Y, and P sub Y is less than equal to R sub Y. And finally, P sub Z is greater than equal to Q sub Z, and P sub Z is less than and equal to R Y. Now, I mean, that's really making some bold assumptions here that R is in fact greater than Q and so forth, but that's the basic idea. Obviously, you can go around and make sure that R is greater than Q, and if it's not, flip the points, etc., etc. But that's the basic idea, and it works when our shape is, bound to the proper axis. But what happens when our shape starts to kind of get all fumbly and not bound to the axis? It starts to actually rotate. Well, I don't know how to draw that. Rotate. Rotation. Looks like a yin and yang symbol of a box. Well, it doesn't work too well because then our points look closer than they are, and these points always represent a box as opposed to something that's rotated. So, I mean, if this corner is closer and this corner is closer, it's still just going to give me a box here. And if I guess I can draw a better example of that. Even with my limited drawing abilities, we take this box and we take this one, we're still going to get, some, flat box. And I guess I'm not very good at drawing that, so I'm not even going to attempt to. But I encourage you to at least try it, whether you use the built-in method in the studio or you're going to essentially write your own. But I don't recommend that you do, because we're going to be writing a better one. So how do we solve this problem is kind of the question. Well, the way that I solve it anyway, or would solve it, am solving it, is to do something called, well, I suppose it's not so much a plane intersection, but it has to do with planes. So first off, let's cover planes. Planes. What are they? Pretty much they're just a surface in space. I mean, surface can be anything. So if I have my X, Y, and my Z, not very good at drawing, I cannot stress that enough. Right, I can have some surface, and I'll change my color to help encapsulate what that surface really is. It's just a slightly lighter green. This is, or darker green, sorry. This is rotated kinda, and it's going all over the place in terms of these axes. And it extends forever, but I can't draw forever, so it's not really a box, but this does in fact extend forever. So if you want to think of it, it's kind of like, you know, the surface of a table, or you know, your wall or something. It's a flat surface. It doesn't curve, unless you have a curved wall or a curved table, but pretend you don't if you do. And it's flat, and imagine it going on forever. And I mean, you could rotate your table if you can pick it up, assuming it's light enough, and you can make it any which direction you want it to, and you can't so much do that with a wall, but you can sure as heck imagine it. So a plane can be really any surface in space. I mean, I don't know how much else to describe it. If you're still having a little bit of difficulty understanding my description of it, which, don't misunderstand, I think is definitely possible, go ahead and give it a Google, because you will probably find better examples that aren't hand-drawn, because drawing in 3D space is tough, at least for me. So, there's two things we need to define a plane. Two defining factors. Factors of a plane. And those two defining factors are going to be a normal and a point. Now the normal, for those of you who don't know, is essentially if I take a surface, once again, imagine this going on for infinity, but it doesn't even need to, it could be literally a box. It's just the direction that the surface is facing. So I'm going to draw it as a vector, right? It's 90 degrees, it's perfectly perpendicular in every which way, right? So there's 90 degrees here, there's 90 degrees going up. It's 90 degrees to the surface. If you want to think of it, hopefully you do have a flat table and not some weird curved one. You can put your hand on the table with your thumb pointing up, like you're giving a thumbs up, and your thumb is in fact the normal vector, right? You're putting the bottom side of your hand with your, you know, the flat of your pinky on the thing, and your thumb pointing right up to your ceiling, and you've got your thumb, which is your normal vector, or the normal, well, your thumb isn't the actual vector itself, but it's the direction. And that's what this is. You can do that, obviously. Once again, you could pick up your table and rotate it which way. As long as you're putting your thumb on the back of that table, it's still going to be pointing where the face of, you know, this surface is pointing. Now the point is just some point on this plane. It could be here, could be here, could be here, could be here, wherever, anywhere on the plane. And remember, these things go on for infinity, so it could be over here, it could be up here, it could be over here, here, here. It really doesn't matter. The point is, no pun intended, we can apply the normal to that point, and because we know that the plane, this is 90 degrees, remember the normal is 90 degrees at all times. If we get any vector that is 90 degrees, we just apply in that direction. And if I, you know, draw another one here, 90 degrees here, we just apply some scalar to these directional vectors, and voila, we are on the plane. So this guy kind of handles our rotation and what have you, our orientation, hope I'm spelling that right, of our plane. And so with that, we can actually do some interesting math. And so far I've gone over actually really explaining just how we can define it with a point and a normal, and we're going to be doing that in a way, per se. It's a little different than that, the way that we're going to be handling it, but it's still the same idea. And I'm going to get my straight line tool here, and I'm also going to change my color up. Let's go with some dirty yellow. So I'm going to draw this. We're going to do this in 2D for the time being. We'll say these are our axes, so say this is X, this is Y, and I don't know why we switched to 2. I want that to be thicker. Right, so this is still, though, I mean, I'm showing you this kind of like facing it. There still is depth. I mean, it still exists, but I'm kind of phasing it out here just to make it simple. So this origin point here is still, in fact, 0, 0, 0. And what I'm about to show you does, in fact, apply to 3D. It's just easier for me anyway, to draw it in 2D because I am not a hand-drawn graphical wizard, clearly. So we'll say this blue line here is our plane, and remember this bad boy extends for infinity, and it's also, remember if there was Z, it would be going out in that Z direction here, which I can't really draw depth once again. So it's just we have that perfect side view where we can't see the depth because our perception is just perfectly in line to kind of phase it out. So we have our plane here, and we have some normal to this plane, which once again I'll slightly change our color here for that normal. We'll just draw it up out here, and I don't know why it keeps changing me back to a very tiny thickness. That's quite annoying. So we have some normal here. We are going to call that n with a hat. The hat means that it's a unit vector, meaning that it has a magnitude of 1. And recall this is 90 degrees to this plane. Now I said that we need a point to define our plane. Now this is where things are going to get a little different. So what we're going to do is we are actually going to have some amount, some distance from this origin to the plane. It's going to be perfectly in the same kind of direction as n, if you will. The same, like it's not angled like a different way. It's not going like this, and it's not going like that. It's in the same kind of direction as n. But it's not a vector, it's just the length. And we're going to call it d. And what this is it's a negative value because n is going in this direction. It's a value that we can apply to d. So if I say d times n hat, I'm going to get a vector that is the same length as d but going in this direction. Right? Because if we take a negative and a negative scalar and multiply it by vector, we're going to get the opposite of that vector. And if we have this particular distance between these 2 points, then it's just going to give us this kind of vector in the end. So that's what D is, and we're going to worry about getting D later. So don't worry about how we actually get D. Just know that we have D, and that's how we're defining our point essentially. So the distance is realistically to get this point, just to clarify some things, it would be negative D because D is already negative times n hat, and that would give us our point. So we're just assuming that we do have, in fact, D. Right. So what we're going to do from here is we're going to project, or I suppose we need a point. I shouldn't skip that step, that's rather important. So let's say we have a point, and what we want to know is if this point here is this point here above or below. Ooh, I always forget if there's 2 L's or 1 L. I'm gonna go with 1. Playing it risky. Below the plane. Relative to the origin. And all I mean by that is because I'm saying relative to the origin, I'm assuming that the origin, so anything underneath, or what I'm calling underneath, anything on the same side as the origin is considered underneath, anything on the opposite side that the origin is on is considered above. So, oh boy, a lot of control Z's. So what we want to know is this point on the opposite side of this plane relative to this point, or is it on the same side? Now, I mean, visually speaking, we can easily see that it is quote-unquote above, but how can we prove it mathematically? Well, kind of gave you a little teaser already, but what we're going to be doing is we're going to get our good friend the dot product to help us project. Project. And whoops, whoa, sorry about that. What I'm going to do is I'm going to draw first the actual vector. So we have 2 here. Right, some point, that's what the actual point is. It's not just some point floating in space, it's an actual vector. So we'll give that a name too while we're at it. We'll call that P hat, or P not hat, P vector, sorry. And we'll once again change the color here to green now. And what we're going to do is we're going to project P onto n. So what we're doing essentially is we're getting the component of p that is traveling in the same direction as n. So what is that? It is, essentially this line. And why am I keep going to these thin lines? Jeez. Back to 1px. We want to be at 4px. So it's essentially, and I don't want to completely overwrite d. So it's the same, covering the same distance as d, and it's going straight up, right? And we're getting to about this point where this is now a 90-degree turn, and I'll change the color on this to something else because I don't want you to confuse these for the same thing. And that's 90 degrees here. Right, so this green line, this one here, is our projection. And we can get that by simply saying, and this is dot product stuff, so if you haven't read the article on the dot product or don't know the dot product, you're going to need to know that to understand this. But it's going to be p dot n, and it would be divided by n, but because n is just 1, it's kind of redundant. So this length here, which is a scalar value, is just p dot n. So we have our projection here. What we can do with this, which we'll call its projection, I suppose. What we can say about this is if we have d here, which remember is some negative value, and we say projection minus d, or plus d, sorry, because d is some negative value. If we are left with a positive value, that means that we have some value that is above the blue line. If we're left with a negative value, that means that there was a chunk, it wasn't long enough to be essentially passing this blue line. Because, what happens if your d is greater than your green? If your green only goes up to here, negative d plus positive whatever this green line is, it's going to give you a negative number, whereas negative d plus a green line that goes all the way up to here is going to give you a positive number. So we've just done it. We've proven it mathematically. So we now know, very simply put, that the projection plus d not equals, well, it'll equal some number. So I guess I'll write that number. And if that number is greater than 0, then we know that the point is above. Right? And if that number is less than 0, then we know that point is, once again, not sure about the L, below. So, how can we actually apply that to our shape in region 3? Well, luckily for us, when we have a part, we have some properties here. Or when we have really anything, we have a C-frame. Let's say we have a C-frame because that's more general fare, and we have some quote-unquote size that we are going to apply to the C-frame for a bounding box. We can say from this C-frame, either by pulling apart its matrix, which I'm not going to do because that's a pain in the butt, and there's other methods that can more easily get it. We can get the facing directions through things like look vector. Right, that's the front-facing vector. We can get we can get the right. We can get really all the vectors. In the way that I'm going to do, I'm not even going to be using look vector. I'm going to be using vector to world space with the enum normal IDs, just to get the top, bottom, right, etc. All those different facing vectors of a C-frame. So that handles our rotation there. Then we're going to build our planes out of that by using the size, or really size divided by 2, and the components of those size with the, of course, proper vectors that we're getting in return from our vector world space to actually define our plane. Then with that being said, if we have a box, and we'll assume this is in fact rotated, here we have a box, and we're defining all these surfaces as planes, right? So even though and I'm doing my best to draw this, even though these surfaces, and this is the top of the box, goes on forever, as long as I'm checking all 6 of these surfaces, and I'm trying to draw these lines kind of in line with the actual surface that I'm referencing here, as long as the point lies inside this box between all these surfaces, it's going to always be below. Well, I mean, depending on how we define it, which we'll do in the code. You'll kind of figure out how we define these things in the code. This part might be a little better when we actually start writing it, now that we hopefully understand the math here. So let's actually hop into Studio and get to it. So I'm just hoping that does that. Okay, awesome. So we're in Studio here. I just want to point out while I'm here, because we have axis angles, and I'll show you kind of his stuff, which works pretty well. It's not perfect, but it works pretty well, and we'll show kind of the flaws of his. So for one, it's a little wide, so like I'm not hitting it right now. The red represents that we are in fact intersecting. I'm not hitting it right now, as you can see, so it's a little slightly off, but it's not terrible. I mean, it's better than nothing, I suppose. It's only maybe 1 or 2 studs off. And we can actually look into his thing. I'm not going to go over all of it, but this, like this is crazy. We're getting into some matrix comparison stuff, and it's just yuck, right? Nobody wants to deal with that. That is crazy. He even says it himself, I think. This is why no one's done it before. It's really mathy, really long, and really confusing. Yeah, well, unfortunately, or luckily, for us anyway, it doesn't have to be. So, let's get into our region. So, I've kind of already set it up just to save us a little bit of time. We need to define the planes. So, how we're going to do this, we're going to define the planes as having a normal and d. So, n is going to be the actual normal, and d is going to be the distance. So, that's pretty easy to do. How do we do it? Let's see. It's going to be, so the normal is going to be the C-frame, right? We've got the C-frame defined up here. Frame. Or sorry, I'm going to change this here because we'll understand that why in a second. We're going to have n C-frame, and it's going to be C-frame, G-frame, right, vector to world space, and vector 3 dot from normal ID enum dot normal ID dot, and we'll start with the top, and then we want, right, so that's going to give us the facing direction of the top surface. We want to set d, right, and because top is just the y component of the size, it's going to be size dot y divided by dot y divided by 2. And this is also going to be negative, right, because it's what we're applying to the normal to get back to our C-frame here. So that's just one thing. We need to do this for all 6 surfaces, so we'll just copy paste through this. Hopefully it won't be too long. 1, 3, 4, 5, and that's 6, sorry. So this is going to be bottom. It's going to be the same for D. Then we're going to go to, let's say, left. That's going to be X. Oops. We'll say right. That's going to be X as well. These are both going to be Z. And these are going to be front and back. Right, so we've got everything defined. Awesome. Now we just need to write something to actually cast our points. So I'm going to use the same kind of thing that he did. So he's got cast part. It'll return true if the part is within the region. I'm not going to go write all these functions. I don't want to build an entire module in this video. I just want to show you the basic idea. And if you wish to do so, you can obviously apply this on your own to create a full module. So we'll just say region cast point, or part, sorry. And the idea is simple. We give it a part, and what we want to do is we want to say the position of the part. Now remember, sorry, this is important. When we did this, we did this obviously all relative to 0, 0. So we need to kind of essentially make our position relative to the C-frame, because that's how all the normals are, that's how all the sizes are, everything so far up here, except for the C-frame itself, is relative to 0, 0, 0. So we need to make the position also relative to 0, 0, 0. So that's pretty easy to do. We just take self C-frame P, or sorry, I've got that backwards, part position minus self C-frame dot P, and that's going to give us that vector relative to 0, 0, so that we can actually properly use it. So then what we want to do is we want to say, let's look at our equation again. Let's look at our equation again. That's going to be, I just need something to drag through here. It's going to be P dot N, so the point projected onto the normal, so let's go ahead and do that. If, so for underscore comma plane in next self dot planes do, so we want to check each plane, right? And we want to say if the position dot the plane plane normal, which is just n, plus plane dot d, and I've got an extra bracket in here, so I'll get rid of that. And if that's true, then that means, or realistically, that's a number, of course that's going to be true. If that is less than or equal to 0, that means that we were underneath our plane, which means we're technically inside the box on this plane. That means that we're technically inside. So what we want to check for is if we're outside, because we know if we're outside the box, or the plane, like above the plane on any of these 6 planes, we automatically know that we are not inside. So we're going to return false. And if we made it through all that without returning false, then we are assumed to be inside. So let's go ahead and check this out. Hopefully, yep, I don't have to change much other than the name here, so we'll change this to region 3, which is my module. Oh, I do need to change how we get the region. So that's going to be region. For now, we'll just say region.new rpart.cframe and rpart.size. Now we can obviously make a from part method if we want to, but we're not going to do that probably in this video because that's pretty easy to do. What did I do? Oops, I didn't return something, sorry. That's quite important. Return region. Right, so if I move this, now this is important because we're going to fix this in a sec, but I do want you to notice that we are working specifically with the center of the object. So as soon as the center gets in, red. But when the center's not in, not red. So we're going to fix that so that it does work for any collision. But for now, as you can see, it's already doing what I did say it would do, because we're comparing the center of the image, right? Or not the image, the part, right? And it does in fact work for the rotated region. So let's go ahead and apply this to work so that it doesn't just do the center. And the way that we're going to do that is by checking the corners of the parts. So that's pretty easy to do. We'll just need a function to get the corners of a part, so get corners and part, and then we're just going to do the same process here with each of the corners, because we know if a corner is inside, then automatically we know they're intersecting and so forth. So what do we want to do? We want to say, first I'm going to get the size, but just the size divided by 2. We'll understand why in a moment, hopefully anyway. And then I'll create a table for the corners. And then we're going to go ahead and do that. So x is equal to -1 and 1, going by 2. And same kind of process here with y and z. So y, z, and there we go. So from here, then it's simple. We just say table.insert, corners, and we want this as a position value, so say C-frame. We want to take the part C-frame, times cframe.new, and it's going to be size times vector3.new x, y, and z, and then this is a position. So after that's all said and done, it's done the rotation. We only want the position value after all that's been calculated. Return corners. And so what we do is we're just going to go ahead, similar kind of process up here. We're going to get the corners, get corners apart. We're going to say for underscore comma corner in next corners do, and sorry, I want that for loop to be in here. We're going to say, not going to be so much comparing the position so much anymore, or we are going to be doing the position, but we want these corners once again relative to the C-frame there, or the origin, so corner minus self C-frame position. And okay, so if it's greater, then we know that this corner is a lost cause. So if that's the case, then we want to break this thing here, that for sure. We also want to say is in region, and we'll say it's true to begin with, and if it doesn't pass this, then is in region becomes false, and then finally automatically we know if, right, as long as one corner passes the is in region test, then we know that the shape is in fact colliding, so we just return true. And then if nothing made it through that test, then we return false. And that's it. So let's go ahead and check it, make sure that our corners are in fact working. So we'll zoom in here so we can see that it in fact is working. And right off the bat you can see already we're getting some improvement here. Right, I can move it out slightly, the corner's still in, and so forth, and they're intersecting. So I think currently stands that says greater than equal to, so maybe I just want to say, because to me anyway that doesn't look like it's intersecting, that looks like it's right on the edge, so I'm going to just say it's greater than 0 as opposed to equal to 0, and hopefully that will fix that. Right, so let's try that. Okay, that's still not quite there. So I guess technically it is one of two things is happening. Either I've done the that's entirely possible, is that I've done the X, Y, Z. Could I have done that wrong? It's possible. But I don't think I did. So I guess, I would have thought that would have fixed it. Maybe it's just so specifically tight there. I don't know, to be honest. So I'm not going to dwell on that too long, just because I don't want to waste too much time with that. The last thing I want to do then is, just because one thing that I know for sure upon looking at this is that if I rotate this box as it currently stands, so I wanted to rotate it like this, I know that the region itself is not going to be updated. So if I drag this in, right, it's clearly colliding, but the script is not updated because the region is not updated. So pretty easy to fix. We're just going to define the region ahead of time, and we're going to say if our part is changed, our part.changed, connect the function in which we do in fact, there's an n in there, function, we do in fact update the quote-unquote reg. And so there's a closing bracket on that, and we can get rid of this. And that should fix that for us. Attempt to call reg. Oh, sorry, I guess I need to define it to begin with. That's probably important. So we need to define it to begin with, and then we are good to go. So, right, it still works the same there. No change in that. The question becomes what happens when we play around with this thing. So let's rotate it. Is that... have I done it so it's always going to be in there? I have. Okay, so let's go ahead and bring that out. And as you can see, as I do that, it becomes out of bounds. So that's pretty much it. I'm sure I'm missing something quite obvious in terms of why it's red when it's just hovering on the edge there. But that's the basic idea there for you. So, maybe I really don't know. That's so weird to me. Anyway, that's what I want to cover in this video. I might upload this in the description if you guys do want it. I'm not going to change it other than this, but I thought that this was an interesting thing worth going over and exploring. So I hope you guys enjoyed and learned something new. Later.